Imagine you have a collection of data to store in your computer's memory. You could use an array, but arrays have limitations. They require contiguous memory allocation, meaning the memory slots must be next to each other. This can be a problem if you need to add or remove elements dynamically. Enter linked lists, a dynamic data structure that overcomes this limitation. A linked list is like a chain of nodes, where each node contains a piece of data and a reference or link to the next node in the sequence. This structure allows for flexible memory allocation and efficient insertion and deletion operations. Unlike arrays, linked lists don't require contiguous memory allocation. Nodes can be scattered throughout memory, connected by their links. This makes linked lists ideal for situations where the size of the data set is unknown or changes frequently. To better understand the advantages of linked lists, let's compare them to arrays. Arrays are static data structures, meaning their size is fixed at the time of declaration. This can lead to wasted memory if the array is not fully utilized, or overflow issues if the array becomes too small. Linked lists, on the other hand, are dynamic. They can grow or shrink as needed, making them more memory efficient. Adding or removing elements at the beginning or middle of a linked list is also more efficient than in an array, where elements may need to be shifted. However, arrays have the upper hand when it comes to random access. You can access any element in an array directly using its index. Linked lists, on the other hand, require sequential access. To reach a specific node, you need to traverse the list from the head, following the links one by one. Let's take a closer look at the structure of a linked list. Each node in a linked list consists of two main components, data and a reference or link. The data component holds the actual value or information stored in the node, while the reference points to the next node in the sequence. The first node in a linked list is called the head, and it serves as the entry point to the list. The last node in the list has its reference pointing to null, indicating the end of the sequence. Understanding the structure of a node is crucial for working with linked lists. It allows you to traverse the list, access data, and perform operations like insertion and deletion. Section 4. Advantages of linked lists. Linked lists offer several advantages over arrays, making them a preferred choice in many scenarios. Their dynamic nature allows for efficient memory utilization, as they can grow or shrink as needed without the constraints of contiguous memory allocation. Insertion and deletion operations are generally more efficient in linked lists compared to arrays. Adding or removing elements at the beginning or middle of a linked list only requires changing a few references, while in an array it may involve shifting a large number of elements. Furthermore, linked lists are well suited for implementing data structures like stacks, queues, and graphs, which often require dynamic resizing and efficient insertion and deletion operations. Section 5. Types of linked lists. There are different types of linked lists, each with its unique characteristics and applications. The most common types include singly linked lists. These are the simplest type of linked lists, where each node points to the next node in the sequence. Traversal is unidirectional from head to tail. Doubly linked lists. In doubly linked lists, each node has two references, one pointing to the next node and another pointing to the previous node. This allows for bidirectional traversal. Circular linked lists. In circular linked lists, the last node points back to the head, creating a closed loop. This structure is useful for applications like round-robin scheduling. The choice of which type of linked list to use depends on the specific requirements of the application. Section 6. Conclusion. Choosing the right linked list. Linked lists are versatile data structures that offer advantages over arrays in terms of dynamic resizing, efficient insertion and deletion, and suitability for implementing other data structures. Singly linked lists are simple and memory efficient, while doubly linked lists allow for bidirectional traversal. Circular linked lists are useful for applications requiring circular iteration. Understanding the strengths and limitations of each type of linked list is essential for choosing the right data structure for your specific needs.